Hello everyone. Today's lecture is gonna be about game theory. I hope you're enjoying the training camp and you keep watching the lectures. I hope you don't get too bored. And okay, let's start with today's lecture about game theory. So here I have already a drawing. What is game theory about? Well, it's about games, but games have many different meanings depending on context, and even inside math, different branches of game theory study very different games. So to us, what will a game be like? Well, basically, to us, a game will always be a directed graph of nodes. Each one special node is labeled as the start, so it is always clear where in which node the game starts. So basically, we can think the graph as each node encoding the state of the game. Okay, and here for the purposes of this drawing of this graph, we are gonna mark each node with a color indicating which player plays in that state. So in each state, one player will have the turn. Here it will be a two-player game, and we will basically study only two-player games, never three or more player games in this particular lecture. Okay, so here we have the red player and the what color is this? I don't know, cyan player, light blue player, whatever. Okay, so let's call them player 1 and player 2. We usually call them like that. Here I have an example just to show that it is not super necessary that each player plays once, at least for the general definition of a game. So here we have a game where there is some special rule. It seems that if red makes this move, because each edge will encode a move, that's why it is a directed graph going from one state in the game to another. So this move seems to magically grant the first player another free move, so that it can move twice, because in this state it's again the red player's turn. So okay, this is basically the game. There's a special node called start, and okay, for the leaf nodes, the game ends, and we will directly score them. We will directly mark them depending on the rules of the game with a score. We will only treat zero-sum games. What is actually a zero-sum game? Well, it's a game where everything that one player gains, the other loses. So basically, most card games or board games are like that, when one player wins and the other loses. And sometimes there are points, and when you win, well, you win by a certain number of points. And you can think of that as the losing player losing by that number of points also. So basically, this means that we can encode the result with a single number. It's not like we have to say, okay, here player 1 gains 8 and player 2 also gains 8. And maybe in another node, both players end up with 0, so that both players would prefer this one. No, that is not possible for us. We will only consider games where, okay, if the result is 8, that means that the positive player, here I will take player 2 to be positive. We always take one to be positive and the other to be negative, just because, as a convention. So this would mean 8 points for player 2, which is, so it's like player 2 wins, but also we keep a score, so it's better to win 10 than to win 8. And here it seems that red wins, but by only 1 point. It's better to win by 5 points, like this. So this would be the best result here for red. And for player 2, the best result would be this one. But maybe they can't achieve that because the opponent tries to defeat them. So, okay, basically there is a theorem called Determinacy Theorem. Determinacy Theorem, which is theorem, which is quite simple for finite graph, which are the only ones that we are going to study. The interest cases of this kind of theorems is for infinite graph, actually, but we're not going to study any of those. And basically, the Determinacy Theorem states that in any game of this kind, there is a perfect result. So these games have a meaningful result. And in fact, we will soon see that for this game, the result is -1. So for this game, basically, the result is that player 1 will win by 1 point if both players play perfectly. What does the result being -1 mean? Well, it means that the red player, player 1, which is the negative in this case, so it wants negative scores, has a certain strategy that guarantees that no matter what the opponent does, the score will be -1 or better. And so if this player is negative, better means that there must be a strategy guaranteeing him -1 or less. -1 or less as a final result. Okay, and the same should happen for player 2. But player 2 tries to gain positive things. So there should be a strategy guaranteeing him -1 or something better. If both strategies exist, then well, basically, it's easy to see that this cannot happen for more than one number. And when this happens, this is the result of the game, because basically both can guarantee at least that. So that will be the result if both choose that strategy. They can both force it. So yeah, that's what it means. And the theorem is that there is always a well-defined result. And how do we compute it? Well, the way we compute it for this kind of games is basically using the minimax algorithm. It's called like that because in normal games where each player plays once, so first player 1, then player 2, then player 1, then player 2, if players alternate turns, the algorithm will have one minimizing step, then one maximizing step, and so on. And the algorithm is super simple, really. All you have to do is go recursively in this game graph to find out the value of the starting position, of the starting node. And you go from bottom to top, and the algorithm is like greedy, super simple. For each player, when you are in a player node, you look at the values already computed for their descendants, for their direct, for each leaving edge, and you take the best value. In which sense? Well, the player that wants positive scores and larger scores, you choose the maximum. And for the other player, here it is player 1, that wants negative scores, you choose the minimum. It's as simple as that. So in this example, if we compute here, the best that we can get is 0 because we want positive scores. So we will not move to -5, we will move to 0. Of course, the leaf nodes are already determined with the game result. So this node has 0, -2, 2, and -1. So the minimum of those, the most negative is -1. So this is the result here. And of course, the optimal move is just to move towards that result. What else? This one, the optimum is -1. We don't want to get to this 8, which is very good for the other player. Okay, here we also have -1. Here we also have here we have 3 because we would prefer this one. And from all of these results, the most negative is actually -1. So that is why -1, as I said, is the actual result of this game. This algorithm is very intuitive. If you've never seen it before, I think you will already understand it, and there's very little extra that we will have to add. Whenever you have a game with scores, you can basically use this minimax algorithm to compute the optimal values. And the way to play optimally is just to move through the edge, realizing that minimum or maximum depending on which player you are, basically. I want to use this example to show this particular situation here, which illustrates one interesting idea, which is that of reversible moves. Reversible moves. This idea is extremely important when studying partisan combinatorial games, but we will not really study those. But the idea is useful nevertheless, and maybe it can inspire you for some problem. A move is called reversible basically when your opponent can immediately make a move that leaves him no worse. in other words, there is an initial situation, let's say this node, and there is a move such that, well, without even looking at all the options of the opponent, there is at least one option that moves to a position that is better for him or equal to the original one. Happens here. The original situation was -1, and there is, if we make this move to the left, red has this move that leaves the same, -1. It might have been a move leaving to -2, even better for red. But the thing is that there exists an immediate response, like, okay, I do this, there is an immediate response doing something that is no worse. Well, whenever you see that, and I will emphasize that we're only looking at this part of the graph. We didn't even have to, we could deduce that this, that I said happened without computing all the minimax first, just by looking at these 3 nodes without knowing the rest of the graph. Knowing that this one has only these 2 edges, like we can deduce, oh, this must be a reversible move. A reversible move is one that has this property. There is an interesting property that if you delete a reversible move from the game, the value does not change. And here you can check that it is actually true. If we remove this edge, well, no value changes, because basically there is no reason to play a reversible move. That's as simple as it is. Okay, sometimes that can simplify things. Okay, and finally about this kind of games, I should mention that we have not mentioned games of chance. That is, games where there is some probability. Maybe you throw dice, or maybe you pick a random card or something, or throw a coin, something like that. But they fit perfectly into this model, and you can still use the minimax algorithm. So, for example, you can use the minimax algorithm for backgammon. So there is a well-defined optimal strategy for backgammon. The problem is that the game tree or the game graph is huge, but basically, in principle, it is well-defined. Unlike other kind of games where there is not complete information. We will only see games with complete information. Okay, so what would be a game of chance? Well, it's just like these examples, but there might be extra nodes. Let's put them in yellow. There might be, yellow, special nodes, which are not one player nor the other. They are like the world, the universe, or the dice, let's say. They are dice nodes. When you get one of these chance nodes, actually the one who plays it is the dice. So these chance nodes will actually have output just like any other node, but the outputs will be labeled by a probability distribution. So maybe this one are all 1/4. So this is like a 4-sided dice, a 4-sided die. And basically this models the game. The game is just like I described before. You move until you get to the ending and check the score. But the rule is that if you get to a random node, then the dice will be thrown with the probabilities indicated, and the game will progress to the corresponding node, which might be anything. Might be another throw of the die, might be a move of a player, of another player, etc. So for example, this is something like choosing at random who plays next, something like that, and the situation. Okay, when this happens, you can use the minimax exactly the same, but you have to weight the scores for the dice nodes. So here, for example, if the scores were 5, 1, 2, 0, let's say, I would have to make a weighted sum. So I take a quarter of this score, a quarter of this score, and so on. And here I would get a score of 2. So this is the average score, the expected score at this node. And okay, so basically there is a well-defined result for this kind of games where the result will be will now be the expected score. And the argument, it's slightly subtler, but it is very similar to the previous case. Each player will have some strategy. Now it is probabilistic, but each player will have a strategy just following the edges indicated by the minimax, guaranteeing them an expected score at least as good as the result that the minimax computes. And so basically, yeah, in terms of expected score, no player can do better. So that will be the expected score if both play optimally. An interesting special case occurs when the leaf nodes that have the results are only labeled 0 or 1, like indicating, you lose. From the perspective of the positive player, this would be you win or you lose. No other reasonable outcome. And then the final expected score is the same as the win probability for the positive player. So that is quite common to see, actually. That's a special case, but a very common one. If you're interested in the Minimax method, I encourage you to look up alpha-beta pruning, which is actually quite a bit like branch and bound, and it's a very common method for pruning the search during Minimax in order to avoid looking at the whole game tree or game graph. Because I presented the result in such a way that we have explicitly the full graph, but very often the graph is implicit and is constructed or defined by the rules of the game itself, and it would be great to avoid having to check the whole graph. So this is a very common and useful pruning for that. But apart from that, let's having presented this kind of games as the Minimax algorithm, which basically, in principle, if you could create, if you could run for infinite time and create huge graphs and do not worry about runtime, in principle, the Minimax algorithm is enough to solve any game that we will face. Because all of the games that we will face can be encoded like that. But the problem is the runtime. So we want to study more special games and find better ways to solve them. So we will now restrict our attention for the rest of the talk to combinatorial games. So what is a combinatorial game? Well, we will add a few characteristics. The first one is no chance. Fortunately, I just presented how to introduce dice into the Minimax method, and that worked without any problem, very easy. But for combinatorial games, it's essential that we have no chance. We will not allow dice. Okay, what else? Players will alternate turns. So it is player 1 turn, player 2, player 1, player 2. They will always alternate turns. That means that we will not write whose turn it is on the graph anymore. The graph to us will now just look like a directed acyclic graph, and that's it. It will be implicit whose node it is, whose turn it is, depending on who started. If you are here and player 1 start, then I don't know where the move will be, but if you move here, it means that now it's player 2 turn. And if you move here, now it's player 1 turn. And maybe if player 1 had played differently, we would get here, but with the other player to move. So the graph does not specify anymore whose turn it is, because there is the extra rule that it is always alternate turns, simpler. Okay, what else? Terminal positions will be labeled in a particular way, in a very simple way, with either N or P. This is a standard terminology. If you go to see, if you read the Winning Ways or Conway's paper or results in combinatorial game theory, these letters are the standard terminology. N is for next, and P is for previous, and they refer to the player, to the player who has to move. A terminal position will be labeled N if when you reach it and the game ends, then the next player to move wins. And a terminal position will be labeled P. Let's say you have a node P here, if the previous player to move wins. So if we are playing player 1, now it's turn of player 2, now we move, and player 1 would be the next player to move, the one that has the turn. Well, here the winner is player 2, because we reach this node and it is player 1 turn, but the previous player wins. So it's player 2 is the one who has to win. And well, on the other hand, if player 2 here had moved differently and moved here, it would be player 1 turn, but this final node is labeled N, meaning that the next player to move is the winner, and the next player would be player 1. So for n nodes, well, the next player wins. So in this case, player 1 would win. So here, player 2 faces an important choice. If he chooses this one and moves to a P position, he wins, because he is the previous player, and he will win. But if he moves here, the next player, which is player 1, will win. Okay, so this is the structure that a combinatorial game will always have for us. Well, why are they called combinatorial? Well, basically, the crux of combinatorial game theory is to study what is called the sum of two games. When you have, let's say you have a very simple game, like, I don't know, maybe it is this graph, an initial position and a second position. And you have, I don't know, another graph. I will use different letters just because, where you have something like this, and the positions are labeled somehow, N or P, how we learned. Okay, in this case, the sum of the games is a new game, sorry. And how is it played? Well, let's suppose this is the starting node and this is the starting node. Basically, it's like putting both graphs on the table and playing both. So you have one chip or one token or whatever, or an arrow pointing, whatever you want to use to mark where we are, one on each game. And basically on each move, you can choose one of the games and move. That is the rule. That is the way that you construct the sum. So the sum of this game and this game would be a new game where the state is modeled as an ordered pair. So basically the state that these two arrows are drawing is the state A, C, because we're on A in the first game and on C on the first game. And basically from this, you can create a new game graph which has the Cartesian product as states, and the transitions are to choose one game and move. So from here you could move to B, C, because we moved this arrow and not the other. If we instead choose to move to D, for example, we would transition to something like AD. And we could also transition to AE. And basically from this one, we could change only to BD, and there are no more moves. And from this one, we could change to BE, and there are no more moves. And from this one, well, in a very similar way, we could transition to to these ones, which are far away, this or this. Okay, my drawing is very ugly, but this is the idea. So if you know what it is, basically it's almost the same as the Cartesian product of graphs. Cartesian product of graphs. If you consider the directed graph of each game, the sum is a new game having the Cartesian graph as the Cartesian product, sorry, as the game graph. And there is a detail that I haven't mentioned, and is that it might be tricky to handle the terminal position, the new leaf nodes, which here are these two basically. These two are the leaf nodes, because a leaf node will be those pairs that map to a leaf node on each of the components, because then we cannot move anymore. So, okay, let's say that this one was a P. Oh, let's use a stronger color. Okay, like this. Let's say this was a P position, this was an N position, and this was a P position. Then, for example, this BE, well, or maybe this BD is marked as P here and as P here, so maybe it's reasonable to say this is a P position. But what do we do about this node in the sum? The sum is the game where you play both at the same time. What do we do for this case? In this game, when you reach this position, the previous player won, but in the other game, when you reach this position, the next player won. So what do we choose to create the new game? Well, basically there are two ways to solve it. You can use the normal. Basically, the approach that is used is that when we are summing games, when we are going to sum games, we will basically ignore the the terminal nodes. Or better said, we will have a strong convention and we will not be able to choose it freely. So let me say that again. When we don't care about the sum of games, and we are only considering one single graph at the same time, and this is the main graph of our game, then we allow that at the leaves we put P or N, whatever we want, in order to better model the rules of the game. Because maybe the rules of the game don't have all the leaf nodes as P, nor all the leaf nodes as N, although that is the most common case. We allowed that some leaf nodes are P and some leaf nodes are N. It doesn't change most of the algorithm. But as soon as we want to sum games, and basically the most interesting and the most important part of combinatorial game theory is to sum games, then having a situation like this where we don't know what to do with the terminals is very problematic. So we have two options. We choose the normal rule, and in the normal rule then we restrict all the games, the originals one, the sum, all of our games, to the rule that leaf nodes, terminal positions are always P. That is the normal rule. The normal rule is that terminal positions are always P. The previous player wins. So the player that cannot move and reaches and is faced to and has to move, but the position is a terminal position, loses. The player that the previous player, the one that just made the last move, is the winner. And there is also the misère rule, which I think is written like this and comes from French, but I don't care about the word, but this is the word that is used in game theory. The misère rule, I think in French this means basically misery, and we will later see why it is called like that. But the misère rule is that the opposite. We will choose to label all terminal positions N. So the player that cannot move wins. The one that makes the last move loses. So depending on which rule we are using, the sum and the original games too will have this final position as P or as N. Now there is a detail that I haven't mentioned, and the games I've shown you, this example of graphs, are impartial games. So we are dealing with impartial combinatorial games, and we will only see examples of, we will only study impartial combinatorial games. What would be a non-impartial? Well, they are called partisan, actually. What would be a partisan combinatorial game? It would be a game where the graph has edges in two different colors, because you will actually care about the moves that you allow each player. Like before, we had a red player and a cyan player. And from each node, there are edges that only one player can use. And the same for each player. If there are edges that any player can use, you can model it like this, and no problem. So basically, that is the difference. A game is partisan when you allow this kind of coloring, so that from a single node, there are moves that only one player can do, and the set of moves is not the same for each player. That's the main difference. For example, chess and other or checkers or other similar games would be partisan, because the rules say that from a single position, the white player always moves the white pieces and the black players always moves the black pieces. You cannot change that. So they don't have the same moves. You might think that this is a moot point, because actually you can change a partisan game to an impartial game without changing the essence of the game, because you could duplicate every node in order to model in the state of a node also whose turn it is. So basically, instead of having a single node, you would have two nodes for the same game position, but one says, okay, that position with black to move, and there says that position with white to move, so to speak. And so in this node, you put all the edges that correspond to moves that black could do, but not the white ones. And in this one, you put only the white ones. And of course, if the game alternate turns, then this move from white actually will land in the corresponding node for the ending position, but with black to play. So like you duplicate every node, and it's like bipartite, so to speak. And this will magically encode who plays. And now you can think that it is an impartial game. Well, the rule is the same for each, whoever gets to play in this position, because it's like on the side of the board you actually put a marker which says, okay, whose turn it is? Black. And the rules of the game is to make a move for that player but then swap the marker. And now it's like an impartial game. Well, this is true, and this is the reason why many times we don't really, this distinction is not important, the impartial versus partisan distinction. But again, the most important thing and the crux of combinatorial game theory, and what makes everything very, very interesting and nice and worth studying, is the sum of games. And the thing is that this game, in the partisan version, and the impartial equivalent, so to speak, behave totally different for the sum of games. Because when we sum games, we want to keep these colors. So if we have two chessboards, and I play on one of them, I always play moves of my color. So no matter how the turns change, my color is always the same. So as soon as you start adding up games, this trick doesn't work anymore, and the situation for impartial and partisan games is totally different. I will say that the theory of summing partisan games is much more complicated, and we will not see it, but I will leave references where you can read a lot if you're interested on that. So let's continue and let's see the definition of P and N positions, because we have labeled conveniently the leaf nodes, the terminal positions of the game, as P or N, depending on the rules of the game. The rules of the game here, for example, let's take this as a starting node. The rules of the game says that if you get here, then the previous player has won. That who has to play now will lose. And here it is the next player who wins, and this one is the previous one. But we can extend that similar idea to all the positions in the game. We can say that we can call a position a P position if the previous player to play, that is the one that that doesn't move now, is the one who has a winning strategy. A P position will be one where the previous player has a winning strategy, and an N position will be one where the next player to play has a winning strategy. What is a winning strategy? Well, there are set theoretical definitions, but I will keep with the very intuitive ones. A winning strategy is a strategy of what to do for any possible thing that the opponent does that guarantees you to all win. If that, like a program, if there is a program that you can code that will well, that would be a computable winning strategy. Mathematically, any strategy that tells you what you can do and that guarantees you that you always win, then that is a winning strategy. So obviously, both players cannot have a winning strategy at the same time, because if you put those two strategies to compete with one another, they would both win. And in combinatorial games, that never happens. Only one player wins. And the games always ends because we deal with a cyclic graph. We deal with DAGs. But okay, maybe there are positions where no player has a winning strategy. That might happen in other games, but in combinatorial games, there is also a determinacy theorem that every position is either a P position or an N position. Exactly one player has a winning strategy. And if you think of these final positions as either 0 or 1, with being a little careful, you basically can conclude that from the same idea as the minimax algorithm, and we could possibly use the minimax algorithm if we labeled things slightly differently to compute the P and N position. But we will basically give an actual recursive dynamic programming algorithm to compute P and N position, which is very intuitive. And the rule is very, very simple. Well, you first start with the terminal nodes, because those you labeled according to the rules of the game. But having those as the base case for each node, if you can move to a P position, you are immediately an N position. So this is a rule. If you can move to P, then you are an N position. This is rule 1, so to speak. This is very, very intuitive, because this means that for your node, there exists some move where in that node, for whatever reason, you already know that the previous player has a winning strategy. So continuing from that node, there is a way to win no matter what the opponent does for the previous player. And of course, if you move there, you are the previous player. So basically, moving to a P position is winning. And the other rule is much easier, except for the terminal positions, which we have to deal first. But for all the others that are non-terminal, if you else, basically, if you cannot, then you are a P position yourself. Which means that if you start at that node and have to move, well, you lose. You don't have winning strategy. The previous player has winning strategy. And that's it. And that is very intuitive, because if one doesn't hold, then all your moves will be to end positions, because by induction we already know that all are labeled. And so wherever you move, the next player, which is the one you're giving the move, will have a winning strategy, so you will not be able to move. And this is a very easy rule to apply. For example, here we can move to P, so this is N. Here we can move to P, so this is N. Oh, I didn't check it, but the rule is correct for the terminals, because well, the way that we labeled them before, P or N, is perfectly consistent with this definition of winning strategy. So P positions are one where immediately your winning strategy is do nothing and you win, and the terminal N positions the same. The winning strategy is do nothing, and the rules say that you win. Okay, and finally the initial node cannot move to a P position. Whatever you do, you get to N position, so this is P. We sometimes say that this is a losing position and this is a winning position. But the standard game theory terminology is P for previous player and N for next player. For moves, it is actually winning or losing. For example, here both moves are losing. And this is something that characterizes P positions. In a P position, you don't have winning moves. All your moves are losing, which is very logical. However, in an N position, there might be losing moves. The critical thing is that you have at least one winning move. Here, this is a winning move because you move to a P position. If you move here instead, well, that's a horrible blunder and you lose, because the opponent moves here. He is the previous player now, and thus by the rules, he has won and you have lost. So here winning moves would be this one. Oh, there aren't many. Okay, I think all the other moves are losing. So these are the only winning moves, basically. Interesting. There are if you start here and you start here, you win, but you don't have to move. You just start and okay, the game is already finished, and the rules say that you lose. Oh, sorry, this is obviously a winning move too. Okay, so basically a winning move is a move to a P position. This is enough intuition. Okay. I should also say that this is one way to compute the P and N positions, but another very important way to compute them is using the universal property. Well, it's called like that, universal property of the P N positions. And basically, the rule is like this. Let's suppose that you somehow, it doesn't matter, basically you guess it. You somehow set all positions to P or N, whichever way you want. For example, I start in this graph and I say, okay, I want to paint it such as this is N, 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 and these ones are P's. Just because that is my plan. You paint it whichever way you want. Okay. Now, once you do that, if the way that you selected P and N positions for all the positions in the game satisfy these three problems, these three properties, then they must be the correct P and N positions, which is very nice. The first one is that terminals are okay. You must have labeled the terminal positions correctly in the way that I previously described. So for those, you don't have a choice. But otherwise, basically, the two things that you have to check is that the rules are satisfied. And the rules are that from P, you can only move to n. Another way to say it is that from a p position, from one position that you have chosen to call p, you must only be able to move to n. There must not exist ever something like pp. This is completely forbidden. And the other rule is that from any n positions, which is not a terminal, terminals are handled by the first rule, from any n positions, you can move to a p position. So for any n position, there must exist at least one p position from which you can move. Any way, no matter how you get it, any way of setting, of choosing p and n positions that satisfies these properties is the correct partition into p and n positions according to this definition. So we might call it a candidate. In step 1, let's say that you somehow choose the letters p and n for each node in whichever way you want, and that is like a candidate solution. Then if the candidate solution satisfies these 3 axioms, so to speak, it is the correct one. So here, for example, the one I chose is terrible. It fails at the terminals, so it is already wrong. Well, this was not a terminal. It fails to follow the rules of the game for the terminal position, so this is already wrong. But it fails everywhere. For example, here, this is being labeled as an n position. So according to the rule, for the actions to hold, there must be a move to a p position, and that doesn't happen. The moves are only this one, and they are 2 things I labeled as n. So that means that this labeling that I chose doesn't work. And you can check that absolutely nothing works except for the correct one. So this is an interesting check. And this is very useful because in many problems, once you have guessed the pattern, probably because you do little small cases and you discover, oh, okay, the p positions are mod 3 or something. You discover a pattern. Then proving that the pattern is correct is very easy using this property. You just have to check that these 3 things are right. And if that is correct, then your guess is correct. And you can have a total confidence when you code it. So let's now study a real example, an example of a subtraction game. Subtraction games are very well known, and a subtraction game is a game where the state of the game is simply a number, and the number encodes how many stones there is in a heap of stones. And there are some numbers which are the allowed moves, and an allowed move is to remove a certain number of stones from the heap. For example, we will see the subtraction game 1, 3, 4. In the subtraction game 1, 3, 4, the allowed moves are to subtract either 1, 3, or 4, but not 2, nor 5, nor anything else, piles from the stone. And we will use the normal rule. That means that terminal positions are p. If you cannot move, you lose, basically. It is easy to see, since 1 is always an option, that the only terminal position is 0. When the pile is empty, you cannot move anymore. But otherwise, you can at least remove 1 stone. So I will start by labeling 0, a pile of 0 stones as a p position, because that is the normal rule. That from that position, if you have to move, you lose. And then we can follow the rule that I explained before and just see the pattern for small moves. This one can move to p, so it is n. But this one can also, so it is n, and this one can also, because it is so it is n. Because of the recursion, I would have to check all of the leaving edges for this one and see if any of those has a p. But and the same for this one. But even if I haven't completed it, for example, I don't know this one yet, I know that here it is a p. So I can already say that this will be an n, regardless of whatever this is. For 2, the only option is to move here, because otherwise we would go to negative. And so there is no option to a p position, and this must be a p position, then it can only move to n. For 5, we can reduce to 3 and get this, so this is also n position. What else? For 6, we can reduce 4 and get here, so this is also n position. For 7, we can only get to n position, so this must be p position. And similar to before, this one has to be n. This one has to be n, because we can reduce 3 and 4 and get to a p position. And in 9, we can only get to 8, subtracting 1, to 6, and to 5. They are all n positions, so this must be p. And this one subtracting 3, you get, so this is n. And well, it is very easy to check the pattern here. You will actually see p and p for n's, p and p many n's. And since the rule for computing something only depends on up to 4 previous values, once you have a sequence of 4 values that appears again, you can be sure that the patterns will always repeat. So this would be enough of a proof. But let's suppose that we had never done this table and we have like some, I don't know, let's say super magical intuition, and I guess, oh, okay, the answer will have to do with mod 7. I am pretty sure that p positions are those that are 0 or 2 mod 7. Mod 7. And the n positions are all the others, 1, 3, 4, 5, 6. Well, you can actually check that this partition satisfies the universal property. And those, even if I never make the table, if I start by doing this random guess because I'm very lucky, I can prove that this is correct because the rule works, and that's the only thing. We can easily check it. The only terminal position is 0, and 0 is 0 mod 7, so it must be p, and it is correct. Then from any position 0 or 2 mod 7, if I subtract 1, 3, or 4, I always get to one of these, but I cannot get from 0 to 2, and I cannot get from 2 to 0, because I will need to subtract 5 or 2, and those are not allowed. So from p, we can only get to n, so we are good. And the only thing we have to check is that from any n position, we can actually move to a p position. That means from any of these remainders mod 7, we must be able to move to one of these. And this is true because from 1 I subtract 1 and get to 0, from 3 I subtract 3, from 4 I subtract 4, and for 5 I subtract 3 and get to 2, and for 6 I subtract 4. So that's it. That's it. I don't have to do any of this if I am an extremely good guesser. And here it was very clear that the pattern would repeat, but sometimes the pattern is something more complex. But you seem to find the pattern with small cases, and then having a way to check it and being sure that it is correct is great. So that is why I emphasize this, even if you don't need it if you're a good guesser, because you will just see the pattern and say, okay, I believe that it works. We could also do this for the Miser rule and see how it changed, and we will see that it changed quite a lot. So basically or at least the important thing is that the values could be totally changed, and they are not simply reversed. It's not like the solution will be n, p, p. No. That's totally false, and I want to make that very clear. The recursion is all the same. This won't hold anymore. The only thing that we have to change for the Miser case are the terminal positions. Now the terminals are n positions. So the only terminal was 0. So for the Miser case, which I will put down here, this will be an n, and that is the only change. So this makes this one a p, because we can only move to a p position. We cannot move anywhere else. This makes immediately this as an n, and this as an n, this as an, oh no, sorry. Oh yes, it was correct. This one is n, this one is n, because 5 minus 4 is 1. This one can only move to this, so this is p. And here we see the pattern again, p and pn, p and pn. So from now on, the pattern will actually repeat. So we get again a pattern mod 7, but it is a different pattern. And you can check by comparing up and down that it is not just as easy as swapping p and n's. No, it's more complicated. And this is a very simple game. In a more complex game, the relationships can be totally different. So I want to leave that out because it might be a common misconception, and I don't want you to have wrong answers because of that. Now, Next, I will show you the power of game theory by showing you that actually the Eratosthenes sieve is a special case of a normal algorithm for games, for computing p and n positions efficiently. I call it the sieves idea basically because of that. But as an example of that, I will speak about Wit of Game. Wit of Game is a very simple game where you basically have a queen in chess on a board, on an n times n board, let's say, and your queen can move up, left, or diagonally up and left, but never in the other directions, like to the right. No, that's forbidden. These are the rules of the game, and basically the one who cannot move loses. So the one who moves here will win because the other one won't be able to play. Okay, great. So how do we compute for each cell whether it is an n or p position? Well, it's easy. This position is a p position because if you're there, you lose. And then you start computing. Well, basically the recursion that we know is that for each node, if we want to know how it is, we apply the rule. So we check, do that node, can that node move to a p position? If yes, it is n, and here it is. Otherwise, it will be a p. And so we can keep doing this. We check and we find the p. We check and we find the p, and so on. And here we check and we find the p. We check and we find the p. But here we check up, left, diagonal, and all are n. So this will be another p position, and so on. We can continue. But basically, this will be an O n cube algorithm. This is like the normal, obvious algorithm from what I was talking before. So filling the table this way will take n cube time because there are n square cells and each one takes a linear time proportional to the column and row, and the diagonal is like the minimum of both. Maybe actually you probably can improve that by being smart and using some kind of data structure or something, or not an advanced data structure, just prefix sums or something like that will do, and also diagonal sums, but that is harder to implement. So we want something both simpler and more general. Because here it is a very nice table, but maybe the movements are very complicated and it's not easy to make a prefix sum. So how can we improve that? Well, with the sieves idea, I will show you what I mean by that. And for that, I will use a fictitious game. Let's imagine that we have this ridiculous fictitious game. The allowed move is to a proper divisor of a game. So not 1 and not n. So the position is a number. And here is an example of the full graph of positions when you start with the number 12. And the only allowed move is to move to a divisor of a number. But it has to be proper divisor, never 1. And of course, you cannot loop to the same number. So what do you do with this game? Well, we could compute, but actually it's very easy due to how simple the game is to see that the p positions, actually p was not previous, it was p of primes. The p positions are actually the primes, and it's easy to see because from a prime you cannot move because they have no proper divisor. So by the normal rule, I never said this, but we're playing with the normal rule, so you cannot move, you lose. So immediately primes are p positions, and if you don't have a prime, at least if your number is 2 or more, we're only dealing with numbers 2 or more, then your number is composite and it has at least one prime divisor, and so you can immediately move to a p position. That makes all the other positions n. So computing the prime numbers is identical to computing the p positions of this game. But then we can see, okay, we know that there is a very efficient algorithm for primes, which is the sieve. So let's see what the sieve does and see if we can draw inspiration from that to get a general algorithm for games and p and n positions. Well, actually, you could do it the other way around. You think about an algorithm for games and you see, oh, when I use it for this specific game, I get the prime algorithm. And the idea is simple. Instead of going, the key idea why the sieve algorithm is fast is because instead of going to each number and checking, okay, let's look its divisors. Okay, its divisors are here 2, 4, and that's it. Okay, let's see if any of those was already marked before as prime. Oh, 2 was marked as prime. Okay, so it is divisible by a prime. So this one cannot be prime. No, the sieve doesn't do this because going through all the divisors for each number doesn't make sense. It's better to do it the other way around, just like the sieve does. Whenever you see a prime, okay, maybe this is a terminal position, so you see prime, you immediately go the other way around from bottom up instead of going top down, let's say, and you iterate all the positions that can move to this number and immediately mark all of those as n. Because, okay, if this is a p position, any position that can move to me is n. So 4 is an n position, with sieve just crosses it, and so when sieve crosses out all even numbers, that's like marking all of those positions as n because they can all move to p position. Then we see the next one that still doesn't say n, and we see, oh, okay, it's this one. This one has to be p because if the position could have moved to some p position, I would have already marked it. And now from this one, I immediately, now that I know that it is p, mark all the positions following that can move to this one, which are its multiples, and that is what sieve does. So this one is marked as n, this one is marked as n, etc. And now we continue like that with a topological sort of the arrows in the game, which for these numbers are just in order. And whenever we see an n, we skip it because we already know its value. We marked it before. But the trick is that why sieve is so fast is because it only does the expensive step for the p positions, for the primes. That is the gain. And okay, this algorithm of going in order and then you take the p positions and mark all the others that can move to them as n. And when you see an n, simply skipping it works for any game in principle. You just have to follow a topological sort of the arrows so that you don't fail the recursion, but otherwise it's fine. And if we use it for this game, we can massively improve things trivially without having to do prefix zooms or any diagonally prefix zoom, something complicated. It's not like it's super hard, but this one is trivial. I go like 4-4 because that is topological sort here. That is a topological order. Okay, I see this p. Okay, I mark all the row as n because all of them can move here, all the column as n because they can all move here, and all the diagonal as n because they can all move. I go on with the topological sort. Oh, these are all n, so I skip because again I already know the value. And the first one that I see that is not marked will be this one, and I know that it must be p because otherwise, if it could reach a p because of the order I'm going, I must have marked it already. And now I can do the same. Oh, all the row is marked as n, all the column, and the full diagonal. So you see that I am, with much less effort, I am able to cross out almost all the matrix. In fact, this algorithm is quite practical by hand for these sizes. I've almost finished. Oh, it seems that this one works. Oh, this is not symmetric, so this one is here. Okay, and these seem to be also p positions. Okay, nice. So I've solved it for the full matrix, it seems. And obviously this algorithm is n squared, so we get a better complexity immediately. Why is it n squared? Well, because the n position costs 1, they are immediate, we skip them. And the p positions pay linear time, okay, but there are only n p positions because it's very easy to see that there is at most 1 per row. So that's it. With this very simple using of the sieves idea, we can get a better complexity. So I wanted to show you that. And finally, because before going to the sum of games, which is the juicy part of all of this, I will show you the game of Chomp because I want to illustrate a simple yet interesting idea. Okay, the game of Chomp is like this. You have a rectangle n times m, and whichever player cannot move loses. normal convention, but the move is like this. You choose one cell that is available and you completely obliterate any cell below and to the right. That leaves a new mutilated board. So now I choose this one, for example, I destroy all of this. Now I can move here and destroy only this cell because all of the other is destroyed, okay? And so on. These are the valid moves. But there is a catch. This cross means that it is forbidden to basically play there. It is forbidden to chop this cell so that everything is more interesting. So I can chop this, maybe, but then my opponent immediately will chop all of this and I lose because I cannot move. So I have to try to do something better than that. And this move is the one that is forbidden. So who wins at chomp? Well, playing chomp perfectly against a perfect opponent is quite hard. I don't know if there is. I think that no one knows an efficient, computable, efficient algorithm to play chomp from any given position. I think that is a very hard problem. And even from the starting position to actually play good against an opponent is a hard problem. But there is a very simple argument that the initial position in chomp in an n times m rectangle is actually winning. So it is actually n position. So we don't know how to play, but we know that there must be a winning way. There must be a winning move, even though we don't know which one it is. Why? Well, basically, imagine that you do this move. Then, if this move is winning, perfect. Okay, this move is winning, and there exists a winning move. Now, the remaining case is what happens if this is not the one. This is not a winning move. Well, if this is not a winning move, it means that we must have moved to another n position. I mean, no matter what our position was, if the move that we did is not winning, that means we moved to n position. So from that position, our opponent must have a winning move to a p position. Let's say that whatever it is, let's say that it is this, but you can see from the drawing that any other will do. The opponent will move like that, and so this position must be a p position. But there is a catch. Whatever the opponent moves after my corner move was already a valid move for me in the initial position. Instead of doing this, I could have done this. So I could have directly moved to this p position. And so I get to the conclusion that then, in that case, if this move that I did originally was not winning, there was another move for me that was winning. So in either case, the conclusion is always that, this is correct, that my initial position is n. But I know which is the case, whether the winning move is this one or some other, I don't know. But I know that one of those is winning, definitely. So there must be a winning strategy. This very elegant argument, which is completely non-constructive, it doesn't tell you how to play, but it shows that there must be a way to win. It's called the strategy stealing argument, because basically you steal the opponent's strategy. You say, okay, let's imagine that I do this and the opponent manages to win. Oh, okay, I will take his idea to use as my move and then I can win. So basically that's a contradiction. So I must have had a winning move initially, but I don't know which one that is. And this is the strategy stealing argument. This is like an abstract representation of the situation that we saw before. If we have a position here that we're considering, whatever it is, if we can move to a certain game G, and we can also move to all the options of that game G, then our position is winning, necessarily. That's basically the idea of the stealing argument, of the strategy stealing argument. Here in the abstract position graph, we can easily see it as, okay, if any of G's option is a P position, since we can move to G's option, we are immediately winning. We have the move directly to the winning, to that P position. Otherwise, all of G's options are N, but then G itself must be P, because it can only move to N positions. But then, since we can also move to G, we must be N position. So in either case, we don't actually know. We can't actually know anything about the true status of any of these positions, but whatever they are, in any case, we will definitely be N whenever the graph has like this shape. And if there are other things, other options for us, we don't care. These options are enough for us to be winning. So this is the crux of the strategy stealing argument, which is a very nice idea to know. Okay, now we get to the most important part, that of the sum of impartial games. Like I said before, we will use the normal rule. So all terminal positions will always be P positions. The player who cannot move loses. Like I said before, the Miser case that corresponds to the rule the player that cannot move wins is extremely hard. Everything is much more complicated. So we won't talk in this talk about that case. Maybe a little bit at the end, but it's much more complicated. Believe me, much more complicated. NIM, the game of NIM, will be our natural example for all of this. The game of NIM is a game where you have many heaps of stones. Here I have like 4 stones, a pile of 6 stones, and another heap of 5 stones. And the allowed move is to erase some heaps, some stones from a single heap, basically. At least one. And you can erase everything if you want, but you have to erase at least one, and from a single pile. You can choose any pile, but you have to erase some. At some point in the game, maybe a pile may get empty, but no problem. You can continue, and the one who cannot move anymore loses. Okay, as a notation, because it is a common notation in game theory, we use an asterisk to denote NIM positions. So, like we explained before, summing games is like putting them all together and play in any of them that you want. We showed it for 2 games, but it's the same for more. We will see it now. And so, a heap of a NIM of 4 stones is conventionally notated as star 4. Star 6 would be the heap of 6, and star 5 this heap of 5. So actually this NIM position, this position in the game of NIM can be notated abstractly as a star 4 plus a star 6 plus a star 5 with respect to the sum of games that we mentioned before that creates a new game position. And basically this is true for the game of NIM. Clearly we can see that any NIM position that we are interested about is actually a sum of individual NIM heaps. So naturally NIM is an obvious example where being able to study the sum of games helps a lot, because basically a single heap of NIM is a very simple game. You can erase anything you want. So if you want to win a single heap, you erase everything and that's it. But the options are also very, very simple. From N, you can move from star N, you can move to any star X for X lower than N. That's the rule. You can decrease. So very, very simple. And another convention, just so that you know, star 1 is also written as just a star, because it's such a common in game theory in other contexts. And star 0 would be the zero game, a game where you cannot move, an empty NIM heap. So no move can be done. So it would be, it is also written as 0. And it corresponds to the game where you cannot move. So in terms of graphs, which is what we were looking at before, it would be like this. We can write star 5, or basically just draw this game. It's the same to us. It means the same because this encodes. Oh, sorry. This is actually wrong. I should add all of these edges. You can go to any. So it's the transitive closure, right? Lots of arrows, but you can basically go down however number of stones you like. So this would encode like, okay, this node is no stones here, 1 stone remaining, 2 stone remaining, etc. So we can use, you see now why we don't draw this every time. We can just write star 5. Star is like this graph, it's the same. And the zero game is actually a single node and a start. That's it. That's the graph. This is the only graph that corresponds to the zero game. So this is basically the zero game to us by definition. It's the graph with a single node, and that's the start, and that's it. And okay, why might any of this be useful? Okay, first let's make a clarification. We will consider 2 games to be completely identical if the graph are isomorphic and having the same start. So if you cannot distinguish the graph, they are identical, they are actually isomorphic graph, we will consider both games to be the same game actually. For example, star plus star, 2 heaps of nim of a single pile, is the same to us as this graph. It's identical. It might not be obvious at first, but if you actually draw the possibilities from here, you can move to 0 plus star if you move in the first one. You can move to star plus 0 if you move in the second one, and then from this one you cannot move in the zero game. So from any of those you can actually move to 0 plus 0, and this was the start. So we can check that actually these two graphs are isomorphic. It's the same. So to us, this drawing and star plus star will be identical. We will think of them as the same game. Exactly the same game, not just equivalent or something like that, which we will soon be talking about, but identical. So to us, actually, when I said that a game was a graph, in fact, for the purpose of this part, I will think of a game actually as an equivalence class of all the possible graphs under the isomorphism of the drawing, basically. So yeah, if they have the same drawing, to us, it's the same graph. I'm not being 100% formal, but close enough to being formal. Okay, and basically with this notion of what to us are identical graph, which we take to be the same object mathematically, no matter what that object actually is, don't worry for now. The thing is that to us the game is the graph, and any other graph isomorphic is the same game. Okay, with this idea, then we can actually say that A plus B is identical to B plus A. Maybe if you consider labeled graphs, those sets in set theory are not the same because they have different labels or the construction is not identical, but it will surely be isomorphic. It will have the same nodes, maybe in another order or something like that. So they will be definitely isomorphic. So to us, A plus B and B plus A are the same game. And the same holds for A plus B plus C, grouped like this or grouped like this. Both of these, when you have a sum, it's associative because basically you can say, okay, put all of the games on the table and play in any of them. And that rule is clearly associative and commutative. And this is what we think of when we say, okay, I sum all of these games, just put them all there and play. You can check, remembering the definition of the Cartesian product of graphs and what the sum is. You can actually check that these two graphs will be isomorphic. And that is why, to us, they will be the same game. Even if the sets are not identical, depending on how you define it, no matter, it's isomorphic. So to us, it's the same. We take it as the same object. And of course, 0 plus A is identical to A because the graphs will be isomorphic. Again, maybe the graphs are not identical because the sum will have ordered pairs. So maybe it has 0 some node A and 0 some node B, where the original had A and B, but the relationships will be identical. It will be isomorphic. This is obvious because when you have a single node and you do Cartesian product, that node cannot move, so it just is there sticking but can do nothing, and so the connections will be those that were in A. So all of this is to say that with this, the operation of game addition, this plus, basically becomes a commutative monoid over the games. So it takes two games and it produces a new game in this sense where we don't care about isomorphic and we call it all the same. And in this sense, it becomes a monoid. And 0 is the neuter element. We can actually see that it's a monoid and there are no inverses, so it's not a group. There are no inverses, you cannot subtract, so to speak, because, for example, if I have, I don't know, star or something like this, which is this drawing, there is nothing that I can add to this to create the neuter, the 0 graph. Because the 0 graph, by definition, would have to be a graph with a single node, and no matter what I do, I cannot get anything isomorphic to this. So there are no inverses in the sum. Described like this. And one final piece of notation. I will write the result of a game G to mean the result of the starting position. I mean, if the starting position is P, I will say that the result of G is P. And if the starting position is N position, I will say that this is N. So basically, the result is what we're often interested in, who wins the game if both players plays perfectly. Now, we are making progress. Let's really quickly put some formality into all of this, but this is not so important for the algorithms. Let's say that S is a class of games if basically the zero game is in S, so that it's closed, and it's closed because of addition. That means that if you have two games in the class, then the sum is also in the class. Very intuitive property. Some very natural example of game classes of games. Well, the nim positions forms a class of games in this sense, because basically, well, the empty we take it as a nim position. The losing, in fact, is the only it's the final the only terminal position of nim is empty. There's nothing left to do. And the sum of two nim positions is again another nim position. You have some piles, you add some other piles, you get a new valid list of piles, which is the nim position. Another example is many copies of G. For any games, you could consider a class of games formed by the zero game, G, G plus G, G plus G plus G, etc. The class of all of these games is a class of games in this sense. Because of course, if you sum some copies and you add even more copies, you still have some copies of G. And the largest possible class is simply the class of all games. And of course, this is closed by addition. If you sum two games, you get another game. So the class of all games without restriction is the largest possible class. Okay, why would this be useful? Well, it helps us to define the notion of being S equivalent, which is quite critical. This is a critical notion that is studied, in fact, in combinatorial game theory. We will say that two games A and B in S are S equivalent with respect to the class S, which we will write it like this, using the equal sign, because the convention is to use the equal sign for this equivalence and not for what I before called two games being identical, because in game theory it's much more important this sense of equality, the being equivalent, than actual equality of the graphs. When do we say that two games are S equivalent for S? Well, if for any game that you can imagine, if you have that A plus C is in S or that B plus C is in S, any of those is in the class, then basically the result of the game A plus B is the same as the result. Oh, sorry, this is wrong. This should be C. Okay, the result of the game A plus C is the same as the result of the game B plus C. If that happens, and only if that happens, for any game C, we call A and B S equivalent. Basically, what this means in words, and this is the intuitive notion and the important part, is that if you have positions that are actually a sum of games, and if you have one position, let's say A plus C is in S, then A plus C is a position here that is part of the class. Then that position is a sum of games. If you have a sum of games in the class, and you happen to see one term that is actually A, then you can freely swap it to a B, because notice that this is the same sum of game, but swapping A to B. And the result will not change. I mean, if the result of this one was the next player wins, then here the next player wins, and the same. And it goes the other way around. If you somehow know that B plus C is a sum of games, where B is a term and that is in the class, then you can freely swap it to A and it will have the same result. So in words, it is much easier than in symbols. In words, you have a sum of games in the class, and then in any sum of games in the class, you can freely swap A and B, and that swapping will never change the result of the whole sum. The result in the sense that we already mentioned before, the result meaning who wins, the first player or the second one. We write it like this. They are equal with an equal sign, but we put the class here. And we will simply write A equals B if it happens that they are equal in the class of all games. So basically they can be replaced in any sum of games whatsoever. Two games, so notice that it is very strong for two games to be equivalent. It means that in any sum of games that you have, you can swap one for the other and the result of the whole game doesn't change. It's not too obvious that you can get that, but there will be many equivalent games. And these are some trivial properties that I have here. This equivalence with respect to the class is an equivalence relationship. Actually, it is symmetric, transitive, and reflexive. For example, here is reflexiveness. A equals A always. A is equivalent to A. This is obvious because if you swap A for A, you get the same. You didn't change anything. And from this idea of you can swap, it is very obvious that it is an equivalence. Okay, if you can swap A and B and you can swap B and C freely in the class, then you will freely be able to change A and B and B and C. This is you won't have problems with that. What else? This one is important. 0 plus A is always equivalent to A. This is good to note. So 0 works as a neutral element for the equivalence. It doesn't change equivalence. In fact, we know that 0 plus A and A are identical games. So actually, this is just reflexiveness again. What else? If you have two games that are equivalent, they have the same result. The backwards equivalence is not true. Being equivalent is much stronger than just having the same result. I mean, not any two n games will be equivalent. That is totally false. But if two games are equivalent, then in particular they have the same result. This is easy to see because if you put C equals 0, then they have to have the same result. And the last property is useful, is that basically you can freely add a third term and they will still be equivalent. So it works as an equation. You can add something and it works. This is very logical because if you could swap A and B freely, then of course you can swap A plus C and B plus C freely. You can think of this as, whatever you add, E, then, okay, swapping B plus C for A plus C is the same as saying, okay, I'm actually just swapping A for B, and I can do it. So this is very logical again when you think about I can swap, okay? Okay. And then we get finally to the notion of the S quotient. What is the quotient with respect to S? Well, the quotient is the set of all equivalence classes. So we know that this equivalence defines an equivalence relationship. So maybe the class S has many games inside. These are all the games inside the class S. But when we consider the equivalence with respect to S, some of these games happen to be equivalent and will be like in bugs. Maybe all of these are equivalent, all of these are equivalent. Well, the quotient, the S quotient, is simply the set of these equivalence classes. So here in this drawing, the S quotient would have three elements: this class, and this class. We typically write about games and not about the class, but anytime that you write a game like this particular game, if you're actually thinking in terms of the quotient, then this game is the same as this one and this is the same as this one, because you are only interested in equivalent games. So any changing one game for any other equivalent is the same. The quotient is actually the way to formally say, okay, we are looking at the equivalence classes. And why is it useful? Well, because you can use the plus operator among the equivalence classes themselves. Actually, you can say, okay, let's say that I put names inside this A, B, and C. I can actually use the plus operator inside S to add these little dots, which are the games, and I will get other games because S was closed with respect to plus. But I can actually say things like, okay, let's sum A and C, the equivalence classes. That should give another equivalence class. And how can I do it? Well, I take any element of A, it doesn't matter which one, let's say A. I take any element of C, doesn't matter which one, let's say this one. And I see the result in what equivalent class it ends up. And that will be the result of this. So if, for example, these two happens to end up again in A, because they give, no matter which element, maybe not A, but another A prime that is equivalent to A, then in the world of the equivalent classes, which is the quotient, A plus C will be equal to A, again, the same equivalence class. Okay, this is the idea. I don't want to spend more time, but that is the idea of taking a quotient. And the thing is that these properties, especially this one, very especially this one, ensure that this works fine and is well defined. I mean, maybe you worry that if you choose different elements, you will get different result in the class, but this property ensures that that will never happen. So it is very well defined. If you add equivalent elements, you will end up with an equivalent result, maybe different, but not identical, but equivalent in this sense. And that is the important part. So that defines a plus operator that is well defined over the classes. And now we can add in terms of classes. All of this is to say that from now on, whenever I have two equivalent games, I can actually, instead of thinking of the graph, I can freely swap them, because if I am adding games, the definition of equivalence is basically that they don't change, and I can treat this as elements. Without any problem, and work like they were equations, because this especially justifies that I can freely add on both sides and it works like an equation. Okay, so plus is a well-defined operation over the equivalence classes, and that is precisely the S quotient, the equivalence classes with the plus binary operator. And this quotient forms, again, a commutative monoid, and the class of 0 is the neutral element. Because of course, if 0 doesn't change anything, any equivalent element to 0, when you add it, also doesn't change anything. And the class itself, when seen as an operation, that doesn't change anything. And a final remark, I will say that obviously, if you have one class that is larger, then if two elements are equivalent with respect to the larger class, which means that you can freely swap them in any sum of elements in that class, then they will be equivalent with respect to the smaller class, because of course any sum of elements in the smaller class is also a sum in the larger class. And in particular, if two elements are completely equivalent, then they will be equivalent with respect to any other smaller class. That this is obvious. Okay, up until now, everything that I said worked both for the Miser rule and for the normal rule. If we were working with the Miser rule, it would be true. Of course, the quotients and the sets and the equivalence would be different. Not everything would be equivalent to the same things, but generating another set of equivalences, all the properties that I said, and if you check all the proofs, all the ideas, it didn't matter if we were using the normal rule or the Miser rule. We never cared about what the terminal positions were. From now on, almost in each and every result that I will be doing, it will be absolutely critical that we use the normal rule. From now on, everything basically that I say from now on will fail miserably for the Miser version. So I leave it to you as a task to check, and again later the ideas, and see in which part the proofs fail if we actually don't use the Miser rule. But basically everything will start failing right now. So okay, next we have two simple yet absolutely key results. These results will make all the difference basically. And they are two very simple identities, and they have a strategic proof. That is the nice thing. The proof of these results is just playing a game and explaining a strategy to play a game. The first result is extremely nice, and this is a property that you must know. If you sum a game with itself, you consider, for any game that you consider, A plus A is always a P game. That is, the second player wins. If you start with A plus A, unfortunately, you will always lose. This is what is said here. And the proof is super easy. You just have to give a strategy for the second player, for the previous player, to show how he can win. And the strategy is super simple. Since you have two identical copies of a certain game, just copy whatever the opponent does. The game will start with A plus A. Okay, the opponent changes this to A prime. Okay, then change the other component to A prime. You can do that because they were originally the same. So if here in this game you have the option to do some move, you can do the same move here. The opponent then may say, okay, now I will change this one to A prime prime. But again, if the opponent has a move from A prime to A prime prime, you can copy it here, no problem. And if you continue like this, you always have a move. The opponent shows you which move to do and you just copy. that means that eventually it will be you who will make a move to the 0 game, where no more moves are possible and you get a terminal position. And because we're using the normal rule, that means that you will win the game. You, of course, being the previous player at the beginning, the second player. And that's it. This very simple strategy shows that this is true. For any game, the result of A plus A is P. Great. And there is a second extremely similar result, which also has a strategic argument, which is even more powerful because it involves two games. The idea is that if you have any game, this 0 should be P according to our notation. If you have any game such that the result is P, like A plus A, for example, if you have any game such that the second player wins, the previous player wins, then for any game that you consider adding, for any game B that you have, basically if you add A, it doesn't change anything. The result, well, it might change something, but it doesn't change the result. Whoever had a winning strategy before still has it. Either P or N player, doesn't matter. Whoever was that has a winning strategy in B, the same player has a winning strategy in A plus B. And the only thing that we need of A, the one and only thing, is that A is itself a P game. That is, the previous player has winning strategy at E. And the proof of this is also just constructed. Give a strategy. In order to win, in order to win A plus B, it doesn't matter if you're the first or the second player. Let's say you are the player that wins in B. So whoever wins in B, let's take that role. We are that player. We have to show that we still can win A plus B. Well, our strategy is just to ignore A. Cover it with a blanket and make as if A does not exist. And just play in B. Just play the normal game. And if your opponent plays in B, great. You keep A as if it doesn't exist and you just play normally in B. Because you have a winning strategy in B, that means that you can never run out of moves in B. Because otherwise you would get to the 0 game in B and it would be your turn. But that means that you lost. And you don't lose in B. You have a winning strategy, so that will not happen to you. So eventually, before the game finishes, at some point, it will have to be your opponent who first moves in A. But again, A is a P game, so where it doesn't matter where in A your opponent moved, it has to have moved to an N game, and thus you have some answer again to a P game. And then the strategy is simply that you just wait and you play your normal strategy in B, and whenever your opponent moves in A instead of B, you just play to a P position to restore the invariant that you have, a P game plus the B that you already know how to play. And using the strategy, you can check that you will always win. It's that simple. So that proves this. That proves how to win, and that proves the same player will win. And of course, this full result that we've just proved implies that actually, if you have a game where the second player wins, that game is completely equivalent to the 0 game. And this is for any S, for any class that we're interested in. Because basically this is what it says here. For any game, this is actually with respect to the class of all games. There's no hypothesis over B. For any game, you can swap A with 0, because this is of course the same as the result of 0 plus B. So if you can always swap A and 0 in any sum, that is the definition of A being equivalent to 0. Which is tremendously powerful, because this is an effective criteria. You can build the graph of the game, compute whether it is a P or an N game, and that will immediately tell you whether this game is equivalent to 0. That means whether this game can be replaced in any sum with the 0 game. That is not obvious. So this is a concrete computation that finishes and doesn't require to check all the games in the universe, while this is a result speaking about all the games in the universe. For any sum of games you can imagine, you can swap. You can remove A, basically, because swapping it with 0 is the same as deleting it. That's amazing. And we can continue. An immediate corollary of the result number 1, well, and the result number B actually, a corollary of using both is that A plus A is always equivalent to 0. You just have to combine them. And more importantly, you can check that if you consider the result of A plus B, well, if you know that the result of A plus B is P, well, because of the result we just showed, that means that A plus B is equivalent to 0, but we can add B on both sides and get this. And well, because of this first corollary, B plus B is equivalent to 0, we can just drop it. And thus we get to A equals B. And the path backwards is identical or very similar. So basically, we have more general than just checking if a game is equivalent to 0. We have an algorithm now, a finite something that terminates without having to check all the games in the universe, that tell us if two games are equivalent. Two games A and B are equivalent if and only if you play the game A plus B, you make the dynamic programming algorithm, you check the result, and if it is P, if the previous player wins A plus B, then A and B are equivalent, and if it is N, they are not equivalent. This is tremendous. And this is the key of combinatorial game theory, basically. And another key observation is that this green thing over here does not depend on S at all. None of our results use S at all. But this thing over here does depend on S. And that means that the equivalence between A and B is the same no matter the S. This is what it says here. A will be equal to B with respect to any class if and only if they are equal with respect to the class of all games. So basically we can start completely dropping this pesky S symbol now. We can just write equals because it's the same. It doesn't matter with respect to which class you do it, it will be the same. And of course this is one of the things that will be false when you take the Miser rule. That is why that one is so much more complicated. Okay, but we can continue and say even more. Because of this, we have that every game has an inverse now, the game itself. This is basically it. A plus A is equivalent to 0. That means that in the quotient, when you're working in the S quotient or the quotient of all games, the all games quotient, if you sum for any class, for example, the class of A, the class plus the class itself is the class of 0. So that means that in the quotient, classes have inverses, and it's the same. For each element, it is its own inverse. So that means that each S quotient is a group, not only a monoid, like we said before. There are inverses, so it actually has group structure, and every element is its own inverse. And for those of you who knows some facts about math, this immediately imply that the S quotient must be the XOR operation in disguise, because the XOR is basically the only operation having this property. Basically because this is the same as saying that the quotient has to be an F2 vector space, and well, an F2 vector space is XOR. It's just that. So yeah, it's amazing. So we still haven't shown where XOR appears, but because of these properties, XOR has to appear. This must be XOR in disguise. Okay. Oh, and another interesting thing, there is the group of all games, which is the quotient generated by the class all games, the all games quotient. And now we can say that any particular S quotient is simply the subgroup of the group of all games generated by the games in S, because of these properties. We couldn't say something like that before. When we only knew that they were monoids, we couldn't say that the S quotient was the monoid generated, the submonoid generated by the elements. That we didn't know that at all. We know that now because of the group structure and the properties that we proved. Okay, we can now prove three very important theorems that basically will help us play any sum of games. The first one is that if we have two piles of NIM of sizes n and m, then that those piles will only be equivalent. They will always be equivalent. They will only be equivalent if the numbers are the same. So a pile of 3 and a pile of 4 are not equivalent. The single piles of NIM are always non-equivalent games, basically. And the proof is very easy. We know that in order for two things to be equal, it's the same as the sum must be a P game. And it's very easy to check that the sum of two different NIM piles is actually not a P game. You can move to a P game by simply reducing the larger pile to make it equal to the other one. And we know that this position is with 2 copies is always P. So the original game is N, and those 3 is not equivalent to 4, basically. So this one is basically easy, but this shows that there are none of these single piles are equivalent. And then the critical theorem is that for any game, for any impartial finite game, you can find one, and because of the previous theorem, only one number n, such that the game is equivalent to a single pile of NIM of size n. And that is called the Grundy number, the Grundy number of that game. That Grundy number is the number of which counts how many stones that pile of NIM would have. And this is a great result. And basically the proof is basically constructive. There is an algorithm, and the algorithm to compute what is the Grundy number of a game comes from the graph. You take the graph of the game, and to know the Grundy number of a node, you have to know the Grundy numbers of its options first. And then you just take the max, which is the minimum excluded of its options. So you consider all the numbers that appear in its options, let's say 2, 3, 0, 5, and you take the minimum the minimum non-negative integer that does not appear. That is why it is excluded. So here it is 1, because 1 does not appear and 0 does. So this game would be would have Grundy number 1. So the assertion is that if these numbers are equivalent, if each of these options as a game is equivalent to piles of NIM of this size, then this game would be equivalent to a pile of size 1. Basically, we can step through the algorithm for an example, and the idea of the proof is very, very simple. You can basically check it by playing the game. Again, now we are armed with a very, very powerful tool. Anytime that we want to prove that two games are equal, we can just play their sum. And we can check if that is a losing position. And that is something that we can do in terms of strategy. We can give a strategy of how how the opponent can win, how the previous player can win that position. So basically, for the terminal positions, it's obvious that they're equivalent to a 0 pile. They are the 0 game. If you can only move to the 0 game, well, then it's very clear that you're 1. And similarly, if you can only move to lower piles of NIM, then basically you behave just like a pile of NIM of that size. So this would be 2, for example. It can only move to 1 or 0. This one, we don't know this one. We need this one first. So, okay. We have to solve this. This can move to 0, 1, and 2. So up to now, these are either identical or almost identical, let's say. We can very easily prove that they are equivalent to the pile of NIM. But this one is tricky because it can move to 0, 1, or 3. So according to a rule, it's a 2. But why is it equivalent to a pile of NIM? Basically, what we're asserting with this max rule is that these moves that make the number grow, so we are asserting that this one is equivalent to a pile of size 2. But there is an extra move that does not exist for the real NIM pile of 2, that is to grow the number to 3, basically. So what we are asserting when we place the max rule is that these extra moves that don't change anything. And if you remember my intuitive definition of reversible moves, these are actually reversible moves. Basically, since they grow, we know by the max rule that whenever you are in a node with a certain Grundy number, you have options to all the lower numbers. You may have extra options to larger numbers like this. You will never have an option to the same number because it's that's precisely the first excluded option. But you will definitely have lower. So whenever someone grows the number, you can immediately restore it to exactly the same. So basically, you can ignore it because whoever has a winning strategy for the normal nim using this value can think of that as an impile. You don't need to use the special moves, and if the opponent tries to use these tricky growing moves, you just reverse them. That's basically the proof. So it is quite constructive. That is the strategy that we can use to win the game and prove that this is actually an equivalence. So great. And the only final thing that we would need to solve any sum of games is to know what the Grundy number of something is. Basically, we have a rule based on the graph, but we don't want to build the graph of G plus H for two games because the graph of two games is very large. We know that it's like the Cartesian product. It's huge. We would like to have a nice rule that gives us the Grundy number of the sum of games from the original Grundy numbers. And the rule is very simple. You just take XOR. And of course, because of equivalence, it is enough to prove it for the specific case of piles of nim. So basically, to prove this XOR rule, you can actually show that for 3 and exactly 3 piles of nim of size n, m, and n plus m, the resulting game is a P game, which can be done. You can check online proof of the nim strategy, and okay, if you use it for the case of 3, that proves that this rule is correct, basically. Otherwise, you can just apply the max rule to this game and check that if you make the XOR of all the options, because inductively you know that they are already XORs, you will prove that this is the first, this n XOR m value is the first value that does not appear among the XOR of all the lower options, let's say. So it is actually the max, which it has to be because we are arguing that. So using all of this, we can play any sum of games. How would we play a sum of games? Let's recap. We have like a recipe now. If you have, for example, in original nim, it is a sum of single piles, and we know that the Grundy number of a sum is the XOR of the Grundy numbers. So you just since the Grundy number of a single pile is, well, this should be like this, right? A piles of stones. Since the Grundy number of a single pile is the amount of stones, the number of stones themselves, you just XOR all the values, and if it is, and that will be the equivalent pile. So we should say that if you get a 0, you're equivalent to the game 0, and that is a P game, of course, so the original was a P game. The previous player wins. But if you get any other size, since you're equivalent to a single pile, those are obviously n games. The winning move is to erase everything, and so the original game would be n. So a sum of games is a P game. The second player wins if and only if the XOR of everything is 0, which is a great rule. So in many problems, what you have is a rule of often in problems of having heaps of stones or spaces or something like that of a certain size, you have some rule about how to change it and transform it into one or more piles of maybe smaller size so that it doesn't loop. And you can basically use the rules that we know. When you have more than one game, you can combine them using the XOR rule. Even if those games that appear are the option. For example, if you have a game where you have the option of destroying this, that creates 2 new games, one of size 2 and one of size 2, assuming these 2 are independent. But okay, that option would have the Grundy of 2 for this problem, XOR the Grundy of 1 for this problem. So you can actually compute it as long as you have the lower values. And this often leads to a simple for algorithm to pre-compute a table of Grundy values, and once you have them, whatever list of heap size you receive, you can just XOR the Grundy numbers, and that will do. That is basically the recipe. So also often in a lot of problems, you can basically code this. First, I would say that this computation of the Grundy numbers is typically much faster than you think. Like maybe you see like, oh, it's 10,000 or 20,000, the bound, a quadratic algorithm will not work, but the code for computing Grundy numbers in many problems is like a 4, a second 4, maybe a very small bit set, and something super efficient with XOR, which is super fast. So I don't know, maybe the pre-computation is very fast. I've seen, like it's often faster than you expect. And secondly, maybe you can code this, since often it's easy, and just look at the values by hand or just inspect them. Often there is a pattern and you can guess it, and you might be able to prove it using the MEX rule, for example. But even if you don't prove it, if you see, oh, it must be this pattern, it really looks like it's this pattern, then you guess it, and you can solve the problem. About implementation details, how to implement actually computing the MEX. Well, my recommendation is to use do not use a set, because set is super slow and we don't need sets at all for this. Instead, use basically an array of bools or a bit set. A bit set is a very efficient structure for this, so you could actually use that. Basically, what is the trick? The trick is that if you have n options, let's say you have a game, and from this game you have 9 options, n options to which you can move, then your Grandi number is at most, what is it? Your Grandi number is at most n, right? That's it. You cannot have more than n as a Grandi number, because basically, since you have n options, let's say n equals 3, if any of the numbers 0, 1, 2 is missing from that list, then immediately that or something lower will be the MEX and your Grandi number. So we are done. It's 3 or less. Otherwise, because they are exactly n, you will have to have exactly one of each, and so the first one that is missing is actually n. So you can do all of this in implementation by, I don't know, initializing a variable with n. You will assume that the MEX is actually n, which we know that it's at most n, and then you initialize everything with false in a Boolean array of size n, basically, and then you iterate through the options of the game. Okay, you see an option which has Grandi 3, okay, you set that bit. You find an option 5, you set that bit. And just like that, very fast. If you find an option like 20, okay, that is outside the bounds of the array, that's n or larger, so you don't set anything, because you won't need it to actually compute the answer, basically. You keep going, and in the end, what you do is you just make one for loop from lowest to highest, checking what is the first non-marked that you find. If you and when you do, you reset red to that value. For example, here we will put red to 1 and break. This is super fast and efficient. And note that basically the complexity of this is linear, and linear with very cheap operations in n, the number of options, because that is the size of the array. So we really, this, as soon as you put set, this is super slow, while this option is incredibly fast. So I recommend to, if you are actually computing MEX values by code and not by a formula, use this method. Okay, now I want to mention a few variants and tricks. Basically, there is a very simple variant where you sum a lot of games. You have maybe one game here, one game here, one game here, n games. And the rule is not that you choose one game and you play there, but instead you can choose any non-empty subset of them. So you may play in one game, in 2 games, or in all of them. It doesn't matter. You choose any set of game and you have to make one move in each of those games. Then, in that case, how do you know if the position is winning or losing? Well, the position is losing precisely when all of the Grandi numbers are 0. Remember that for the normal play condition, you have to take XOR. But here, if you can choose any, if the move is that you choose any number of games from 1 to n, and you move in all of them at the same time, then in order for the position to be P, it has to have all zeros as Grandi numbers. And this is easy to check with the universal property. If all the Grandi numbers are 0, you have to move somewhere. And moving always changes the Grandi number, because the Grandi number is an excluded number from the options, so it changes when you move. So it will not be all zeros again. No matter if you move one or all or what you move, something will change. So it will not be all zeros. And from any n position, which are all the others. So for any position that is not all zeros, there might be zeros, but there will be at least one non-zero. And you can basically go and check all non-zeros, and for all of them, move to 0, which you can, because from any position with Grandi number n, you can move to all the lower numbers. So 0 is lower than any positive number, you can move. So we have already proved that this rule is correct. You might have to guess it by trial and error, but once you know it, the proof is very easy. It's just checking that it satisfies the property. And another very related variant, you might be allowed to move in a non-empty set of games, but also not all of the games. It is forbidden to move in all of the games. You have to choose 1, 2, 3, n-1, but not all of the games to move, and at least one. Well, then the rule is that in order for position to be p, all of the grounding numbers must be equal. So 1, 1, 1, 1 is also a losing position. This is clear because since you have to move somewhere, the grounding number will change, but you cannot move everywhere because of the rule. You cannot choose all. That's forbidden. So once you change something to whatever you change it, it doesn't matter. You won't be able to move all of the others to in order to match it. So you will move to a position where they are no longer all equals. And similarly than before, if you have any position where the numbers are not all equal, well, you can choose the minimum and basically move all of the others and reduce them to that number, and you will get a position with all equal to the minimum, and you can basically do that. So yeah, this is the way to win in these two variants, and there are other variants like this, but these are the ones that I know well and I can explain to you. So I want to make one example of a problem. This one is from an old Maratona, I think from 2008. Yeah, something like that, but I don't know where to find it. I just remember by remembering it at the time it existed. I don't know where it is. But the idea of the problem is basically that you are playing 3 on a row. So whoever, you can make crosses on an array of what's it called, of cells, and it's initially empty, but here they will show us a game in progress. So this game has already started and there are 3 crosses, and we might continue from this position, and you want to know, okay, who wins if we start here. And the rule here is simply, the move is just pick an empty cell and put a cross. That's it. And the player who wins is the first to make 3 on a row. That is to make a move such that 3 consecutive cells have X. So we face a problem because this game is not whoever cannot play loses. We would like to have it in that form because all of our theory is based on the idea of whoever cannot play loses. And here the situation is different. It's whoever makes this special move. Here the special move is 3 on a row, or maybe 4, it doesn't matter, but you have to create at least 3 in your move. Whoever makes the winning move, that's it, wins, and the game immediately ends. That's a different rule. But in this case, there is a common trick. You can first check if there is an immediate winning move. For example, if there are 2 crosses together, then you can just add the 3rd one and win immediately. So this is a win position. Or the same if there are 2 crosses close by, like this, say. You can put in the middle and 3 in a row. So first you make a pass and check if there is a immediate win. If there is, then you say that this is a winning position, and that's it. Otherwise, we can change the rule of the game and say, okay, now since players are smart, they will never make a move that immediately allows their opponent to win on the next move. They will not do that. They will prefer to try to delay the game and make any other thing. So we might add the fictitious rule that these moves that will allow the opponent to win immediately are actually forbidden. We change the rule of the game and we think, okay, those moves are forbidden, because we know that competent players will actually not do it then, because they lose if they do. So this is the new rule, and here it is easy to see that this condition that you cannot place if that would leave the opponent the possibility to make 3 in a row is the same as saying you cannot move close to an existing X. How close? Well, to a distance of 1 or 2, because if you move at a distance of 1 from an existing X, the opponent can complete the 3rd one, and if you move at a distance of 2, well, the same, he can play in the middle and complete. So you have to move like this ones, at least a distance of 3, 1, 2, 3 steps apart. Then in a single move, the opponent cannot win. But now, of course, the opponent cannot move here because it is forbidden, it's too close. With this new rule, whoever cannot move loses. because the only legal moves then will be the ones that we have forbidden, and those are the ones that allow the opponent to win immediately. So now it is a game with this new changed rule. Now it is a game like the ones we like. And here, for example, well, these crosses are too close together, and so everything is forbidden. So there are no moves. So this is like the zero game. So this is a P position. You cannot move because you will lose. But if you have another board where maybe you have more options, well, when you place a cross, you basically kill the cells near it, and that is the new situation. You can imagine that all of this has been completely destroyed and is not allowed anymore, because now you will not be able to put a cross here. So yeah, you can think of the new game like this. You have to play a cross on an empty cell, but when you place a cross, all cells at distance 1 or 2 are destroyed, because you are not allowed now to put something there. Whoever cannot play loses. And you can observe that this game, naturally, for a very long row, decomposes into smaller independent games. For example, if I have a cross here, well, it kills nearby, but then we have an area of empty consecutive cells here and an area of empty consecutive cells here, which are completely independent. There is no move here that can affect in any way this part, and the same, and vice versa, because this is in the middle and we cannot cross. If we put an X here, well, it doesn't matter. It breaks what was already broken. It doesn't change anything and reduces this. So basically, for a pile of length n, we can choose any index I in the middle, and we can check that will basically move to the creation of new two heaps. One of size, well, if we moved at place I, this would be like I minus 2, because there are I allower and we destroy 2. And the other heap will have size n minus I minus 1 minus 2, so minus 3, I think. So this is basically all the moves. All the moves from position n are to a sum of a game for size I minus 1 and n minus I minus 3. You have to do it for all values of I. But this is simple. You just generate all these options. And what is the Grundy number of this sum? Well, you already know that it is the XOR of whatever the Grundy numbers for these smaller positions are. So this leads to a recursion to compute the Grundy numbers for a batch of length n, right? So this gives a quadratic solution basically, and it runs very fast because you can check that this code is very efficient and very short too. So to solve the original problem, you just check the position to see if there is an immediate winning move. Otherwise, you make the destroying like this to generate the empty running areas, and then you count, okay, how much how many cells are in each of these areas, and you use the Grundy numbers of those values and take the XOR. So this would be a typical complete example of how to use the theory. So now I will tell you about a very curious operation that it is very rare to see and to have to use, but it is amazing that it exists actually. And it is the product of impartial games. There are other products in combinatorial game theory. For example, it is much common to use in combinatorial game theory another product that is for only a subclass of partisan games, and it's totally different to this one, but we will use this one because this is for impartial games. What the heck is the product of games? Well, it is an operation. You take two games A and B and you multiply them and you get a new game, just like the plus operation. But it is much more strange. Basically, when you sum two games, you get a new game that behaves as a whole, and the rule is, well, the game is defined by its options. Where can you move from this new game? Well, for the sum, the rule is that you can move to any option of A plus B, and this is like recursive. Okay, since the plus means that the two games keep side by side, and you can keep doing this operation of moving them together. I can notate it like this: use the plus recursively to define the plus, assuming that I already know how to add the options. And of course, I can also move at B. So the other kind of options is to choose an option of B and leave A alone, and okay, leave the plus sign indicating that in this game they work as a whole, and you can choose one of these to make another move. So for example, from both of these you could move to A prime B prime, but you could also move here like 2 moves in a row in A, etc. This would be like the shape of how the plus operator works. We've already seen this. Okay, the product of 2 games is defined in a very strange way. When you multiply, okay, let's do this. When you multiply 2 games, well, they now behave like a super powerful unit, but the move is stranger than in the plus case. The move is like this. If you want to move in the product of 2 games, well, the move will actually create, you will have to choose an option of A and an option of B. Note that in the sum of 2 games, you choose one of the 2 games and choose an option in that one and move in that one, and only in one. Here, since it's a product, that might be slightly intuitive, just slightly, you have to choose one option in each, and then you will make your move. But your move is not so simple as just moving to the option of A and the option of B and leaving the product together so that you can keep making moves. No, it's not so simple. The definition is, okay, once you choose your options A prime, which is an option of A, and B prime, which is an option of B, then your actual option to the one you can move is to create 3 copies, which are again a product, which means that again those copies are subject to the possibility of using this rule, right? So what are the 3 copies? Well, they're not copies, but slight variations. They are A prime times B plus, and this is the games, the sum of games, right? So we have, you will create 3 new games and you will play all of them independently, but each of those will also be a product in this same sense, that if you want to move in this one, you will create 3 new games, right? So it is like, it has the power of creating new games. That this is a strange rule, but this is as it is. So you will move to A prime times B, A times B prime, and both primes, A prime times B prime. That's it. Those are the options. And this is one example of an option, but like before, your options are all things of this form. Each option is a sum of 3 games for each choice of A prime and B prime, right? And of course, like I said, from this game, you could choose any of these 3 components and there make a move. And so this game would actually decompose into 3 when you make a move. For example, if you now in this one choose to move to, I don't know, to A star and B prime star, it's like the move here would be to A prime times B prime, B star times B prime, plus A times B prime star, the option that you chose, plus both of them, right? But these terms are unaffected, and so those keep there because you chose to move in this one. But the move in this one creates, replaces the game with 3 other games, and this one stays. So this might be another option. This will be an option of the option, right? This is just to emphasize that this is the way the rule works, right? So why on earth would you want to compute, to define the product of impartial games? It is such a weird operation. Well, it is, but actually, no matter what it works for, it has very curious properties. It has very nice properties. Basically, if you work in the quotient, that means you're working with game equivalence and not caring about the exact form, because these games are so huge and so complicated that I don't know their forms anymore. But if all you care about is if 2 games are equivalent or not, then this operator, well, I'm calling it a product, and there's a reason for it. It actually works as a product with the normal sum of games. So if you have A plus B and you do the product of that game with C, that game is equivalent to A times C plus B times C. Wow. And so on, basically. And the neuter for this product, amazingly, is the game star. We already know it, right? Star is the pile of NIM of a single stone. That is the neuter for the product, because let's check. If you make star times G, then what are your options? Well, star has a single option, so you have to choose option 0. Star is the game that can only move to 0. From the pile of one stone, from the heap of one stone, you can just move to 0, no other option. And from G, you can choose any. So our sum will be like 0 times G plus star times G prime for the option, plus what else? Oh, both options, plus 0 times G prime. And oh, I didn't prove it, but you can check that 0 times anything is actually the 0 game again. Well, this is easy, because what options do you have from 0 times G? Well, in order to have an option for this, you need an option for 0, but 0 has no options, has already finished. It's a terminal move. So this is also a terminal place. You cannot move in this game. So this is obviously equivalent to 0. These are equivalent to 0. We can remove it, and thus basically you see that from this product, your move is to a smaller product where the star is still there doing nothing, and you just move to the option of G. So the graphs are like pretty much isomorphic. It's the same game. So that is why it is equivalent. So the star works like 1 and 0 works like 0 in a very natural way. And you might ask, so this means that that maybe now the set of games is a field. Well, basically it is, but the operation is quite complicated. To sum up, we basically can say that plus and product, this strange product that we've defined, makes with respect, again, over the equivalence classes of games with respect to equality, to being equivalent in the sense that we've already described, this forms a field. Wow, a finite, and basically it is the finite field of order 2 to the 2 to the n. Wow, this is weird. These are Fermat numbers, right? 2 to the 2 to the n are Fermat numbers. And what happens is that, for example, if you make star 5 times star 5, you multiply the pile of NIM of size 5 with the pile of NIM of size 5. Well, these are lower than 2 to the 8, right? But this is not Fermat number. So maybe the result of this multiplication has to go to 2 to the 16th. What do I mean by this? The dot operation over NIM heaps will be closed over any over heaps of size up to 2 to the 2 to the n. But maybe not to any other power of 2 that is not Fermat. So just to show you what I mean, if you multiply two numbers, two heaps, right? If you multiply two heaps smaller than 2 to the 2, which is 4, you will get, as a result, a heap of size less than 4. If you do it for 2 to the 4, which is 16, you will get something smaller than 2 to the 4th. But for 2 to the 3, this is not true. You might multiply two things that are lower than 8, let's say, and get something bigger than 8. And the next one that it is close is 2 to the 8. So maybe if you do like 17 times 17, the result in this strange world of the product might be like 200, much larger, right? Because again, unlike the sum, which basically you know that it doesn't increase the largest power of 2 in the digits, for the product, it only becomes closed again, as I said, for these sizes, which are Fermat powers, which is very strange. And basically, for those of you who know about finite fields, this actually is because, for example, the field of size 8, which is 2 to the 3, is not a subfield of this, and it's not a subfield of the field of impartial games, right? It will have different properties, but everything lines up nicely for these values. So I won't go into any detail of any proof about it, but basically I want to give you the rule. If you somehow manage to come up with a product of two games, well, you would like to have the analogous of the XOR rule. We know how to compute in practice efficiently the sum of two games. You know that you take their grounding numbers and it's the XOR. But what is the grounding number of the product of two games? If you know their grounding numbers, what is actually the grounding number of the product? Well, you can compute it, and the way to compute it is to use these two rules, which I will not prove. They are valid, but I will not prove them at all. If you have a Fermat power, like 2 to the 2 to the n, if you have a Fermat number that has this form, and you multiply this pile with anything smaller, so n is lower than 2 to the 2 to the n, then the result is the normal multiplication. Right? So this will be equivalent to a pile, this will be equivalent to star 2 to the 2 to the n times, these two, there's no reason for them to be the same, right? The same n times x. You just multiply them and that's it. And the other rule that you have to remember is that if you have a Fermat power and you square it with respect to this operation, right? You multiply it by itself, then the result is a pile of size 3/2 your power, right? So, for example, a pile like 16, if you square it, it will give star 24. This is the rule, which can also be written as star 16 plus, with the not the natural numbers plus, but the sum of games plus star 8. And this will always happen because basically these are power of 2, right? This is just a way to remember it. This rule is very strange, but you can apply it like recursively to compute the product of any two games, because remember that it forms a field and it distributes nicely with the addition, so you can basically decompose. Just to show an example, let's say I want to do 5 times 5, like I said before that we could. Well, 5 is 4 plus 1. Every time I write plus, it is XOR, obviously, times 4 plus 1. And I can do distributive. So 4 times 4, which 4 is a Fermat power. It is 2 to the 2, so it should give 6. Plus 4 times 1 is 4. 4 times 1 is again 4. It cancels, plus 1. So 5 times 5 should be 7, if I'm not doing calculations wrong. But you might have other numbers which are actually not Fermat powers. So for example, you might have 9 and you want to do 9 times, I don't know, 3. Okay, well, 9 you decompose it as 8 plus 1, and 3 is 2 plus 1, good. But then you will have to do 8 times 2 when you distribute, but 8 is not a Fermat power, so our rules do not work. Right? 8 is 2 to the 3, and this is not power of 2. So we have to decompose it. But luckily, because of the rules, you can decompose the exponent, right? 3 is 2 plus 1. So this is 2 squared times 2. And each of these is a Fermat power. So by the rule that if you multiply a Fermat power by something smaller, you can do the normal product, this will work. So basically 8 can be written as 2 times 2. Times 2, because we want this one. So now we have to use the rule, right? And 2 times 2 will be 3, because the second crazy rule is that for Fermat powers, 2 is Fermat power, you do this, basically. You decompose in this way. So after all of this transformation, we have to do 4 times 3. And we still don't have a... Oh, yes, we happen to luckily have a rule for that, and we can just say, because this is Fermat power, we do 12. But you can check that otherwise, even if it hadn't been solved so easily, this part is smaller. We have reduced the exponent, so you can recursively keep going, and your numbers are getting smaller. By just applying those two rules, you will always terminate. Anyway, I want to leave you. I will leave you in the links for the class an example of source code that I wrote implementing this algorithm, so that you have it in case you're curious, and you can read more in the winning ways or con ways on numbers and games. I just wanted to show you that this exists. Well, here I computed 8 times 2, but of course you have to do the full distributive, right? I just show the hard term 8 times 2. But the idea is you can decompose anything into powers into sum of powers. You distribute, then you have to do product of powers of 2, and then you can decompose any power of 2 into Fermat powers, and so you will have a chain of product of Fermat powers, and those you can transform into other multiplications that you can do recursive of smaller size using these two crazy rules. So just remembering these two rules, you can push forward and solve everything. But yeah, it is very rare that you can actually get to see a product of two games. But it's, I don't know, maybe you're lucky and you happen to discover one, and this is the algorithm you can use. Also, for those of you that are mathematically inclined, it might be amazing to know that this sum can be extended to a product which has even though it is a very weird meaning, it has some kind of meaning in the world of games. So it is quite interesting. So, okay, just as a final remark, I want to leave you with some thoughts about why the Miser case gets so complicated. And basically, well, it is that all that we did was for the normal case, and all they were very nice properties, and well, they will fail, and that is why basically this doesn't work for the Miser case, and that is so hard to do in general, and it does not have such a beautiful general theory. But well, to spell out some of the things that totally break, the equality, the equivalence with respect to specific class of games is no longer the same as the full equality of games with respect to the class of all games. It will not even be the submonoid, correct? For example, you might guess, we knew that in the case of games, well, the equivalence is just the game equivalence. It does not depend on which game you're analyzing. So two NIM positions are equivalent or not, but it does not depend on whether you are going to sum them with some strange game that is not a NIM position. And the group corresponding to that in the normal case is just the subgroup generated by the NIM positions. Well, here is not at all like that. The submonoid that you get by considering the general equal the general case and the general monoid of all games and restricting it to S might not actually be the same as the quotient when you only look at games S. It's like looking at other games outside of the one you're interested in makes the game not equivalent, but maybe they are equivalent for your game. We will see it soon for NIM. Well, our proof that A plus A always is a P game is completely broken, and there is this result we don't know. It might be N, it might be P in the Miser case. It's not always the same. Also, there is no nice relationship. There's a beautiful proof that was critical to all we did, that in the normal case, when a game has a P position, when a game is a P game, the second player loses, then that game is equivalent to 0. You can delete it from any sum of games. There is no relation at all clearly between the result of a game and its equality to its equivalence to other games. There's no clear relation to that. It's all much more complicated. In particular, you will no way just know that a game is 0 by looking at its result, and so we completely lose the critical test that we had. If you want, for the normal case, if you want to test if A and B are equivalent, if you want to test if two games are equivalent, you just play the sum, which is a game. It has a strategy, so you can compute it in principle. You check if it is a P game or not. Well, there is no result like that. If you want to know if A and B are equivalent, then basically, yeah, you have to consider what would happen if you sum any other game and see what happens. And that might depend, their equivalence might depend on which other games you allow. for a small class, they might look equivalent, but they become non-equivalent for a larger class. That never happened in the normal case. So all of this is much more complicated, of course. And again, the fact that this is not always P shows you that now a game is not its own inverse. And there are basically games where the games don't have an inverse anymore. So basically it's now a monoid. It will under no circumstance be a group, the quotient. So of course monoids, general monoids without inverses are much harder to deal with than those that have inverses. We know it from data structures because we can use a prefix sum, for example, for things like the sum that has a negative, an inverse, then the normal sum, I mean. But we cannot use it easily for max because max has no inverse. Well, the same happens here. In the miser case, we lose inverses. So yeah. And also another thing that breaks completely is we don't have the Grandi number result. There are small games, like maybe they have 5, 6 nodes, I don't remember, but there are games with a very small graph which are not equivalent to any nim position, not even an nim pile. They are not even equivalent to a nim position. There is no position in nim that you can say, oh, this game is equivalent to that. No, this is a very small game, but it's not equivalent to anything you see in nim. So studying nim is not enough to study other more complicated games. So you see that the theory is totally different for the case of miser game. I tell you this in order for you to be careful and aware that this case deserves its own attention. Fortunately, in programming contests, when a miser problem appears, it's typically because you're given miser nim, the actual game of nim, the original normal nim, and you have to play the miser version. And well, for specific games, maybe you can analyze them and get to a conclusion because they are easier than the general theory. And that is the case for nim. If you only want to play nim, normal nim and modified, well, okay, the winning strategy is not too hard to get right. Basically, you can check that. You can play like normal. And for example, I don't know, this position, these two are equal, and I add 3, 2, 1. This has XOR 0. So here, the second player loses. So if it is not our turn, we should win. Well, that will be the same in miser nim, basically. You still do the XOR and check if it is 0. And if it is 0, then the position is P, otherwise it is N. With one exception, there is one little exception. Let's show it with this example because I think it's clearer if we see the example. Okay, here my opponent plays and I should win, so let's say he does this. I can easily copy this. Now the XOR is still 0. Let's say my opponent does this. Well, I can easily copy that here. The XOR is still 0. And let's say my opponent now breaks this 2, so to speak. Okay, now we get to a special situation. There is exactly one pile. With more than one stone. So now we can delete it and choose whether we want 0 or 1. So we can choose the parity. And it is easy to see that if all your stones are of size 1, the game is already fixed. You can't choose anything. You will just keep taking turns, deleting, and so depending on the parity, it tells you who wins. For in normal nim, for an even number of single stones, you get a P position, and for an odd number, you get an N position. But for miser nim, obviously, here it is reversed because it changes who gets to the last one. So basically, the strategy for miser nim is just do exactly as normal nim, but when your strategy would leave all piles of size 1, then leave the opposite parity, the one that you would normally not. So here, in order to cancel, I would normally destroy everything so that the remaining game is 1 plus 1. But if we are playing the miser version, I will just destroy 1. So we get this game, and this is now a P position, which is great because I am the previous player. My opponent will take 1, I will take 1, my opponent will take 1, and I cannot move, so I win because this is the miser version. You can check, in terms of P positions, which are the P positions? They must have XOR 0, or all heaps are of size 1. All heaps size 1 and the number of heaps must be basically odd. Because if there is an odd number, then when deleting, you will delete the last one, which in misernym is losing. Okay. So yeah, basically this is the condition. It's the normal one, but for the special case that all the heaps are of size 1, the condition is reversed with respect to normal. That's the only exception. And so when you are actually playing the game, you play like normal, but of course, if you have a losing strategy, there's nothing you can do. But if you're in the winning position, then it will be you which eventually will have the choice to move to a situation with all ones, and then you choose the other option, the one that you would normally not choose, right? Because the parity is flipped. That's it. This is the way to win in normal, in misernym, and luckily it is easy to check. But what you should not be confused is with thinking, oh, okay, for other games it's the same. I just take the Grundy number and use the misernym rule. That fails. That will not be true for any number. You can check that this rule that I am proposing is correct using the universal property. From positions like this, you can only move to positions that are not like this, and from any position not like this, you can move to a position satisfying this condition. This is written somewhat unclearly, this OR. You shouldn't interpret it just like an OR as written, but instead like this is an exception. Okay, when all the heaps are of size 1, then the situation is just the parity, and you win, and you are a P position if the parity is odd. But otherwise, if not all heaps are size 1, it is as always. So 0 is the condition. So you can check it with the universal property. As a curiosity, we could actually compute what are the equivalence classes of the S quotient for the miser case when we consider the class of nim positions. So when are two nim positions completely equivalent with respect to playing misernym, ignoring other games, just considering misernym? Well, you can use this strategy to think what things are equivalent to you or not. And the conclusion you will get is that your equivalence classes will be those of normal nim that you're used to, the single piles. No single pile will be equivalent to any other. This is easy to check. But there are two extra classes, basically. The class of 2 plus 2, that is 2 piles of size 2, and this will not be equivalent to 0. Because remember, according to our rule, this is losing. This is a P position in misernym, because our rule says that just use the normal rule unless everything is size 1, and you can actually check it. If you move here, the opponent can choose parity, and so you lose from this start. But from the real 0, which corresponds to the empty game where you can do nothing, well, actually that is an end position because you immediately win, right? You can't move. So this shows that these are not the same. And also the other equivalence class is 2 plus 2 plus 1, basically, or 3 plus 1. These two are equivalent. This is another one which is not equivalent to 1 because of very similar considerations. In 1, you're lost because you have to move and the opponent wins. You take the last move. But this one, you're not lost. In this one, you can win because obviously you take this one and you get to this one, which is P position. So yeah, but I leave it to you as an exercise to check that these are the equivalence classes. Basically, for the purposes of playing misernym, any nim position is actually equivalent to either a single pile, or this position, or this position. So these are the values. And you can check what the plus operator among these classes would be. Because, for example, you can immediately check that in misernym, 2 plus 2 is not 0 like the normal, but actually it is this position, whatever we call it. I don't know. If we call this one A, then 2 plus 2 is A, which is a different class, right? Okay, that's enough for today. I hope that this is quite motivating to you. Oh, no, I lied. I want to mention one extra thing as a super curiosity. Well, I already said it, but I want to emphasize that, for example, this position, 2 piles of 2, and these positions, 2 piles of 4, are equivalent, right? So that this one is equivalent to this one for our purposes of misernym, because basically they both have piles of size at least 2, so any of them that appear immediately avoids falling into the special case. And the XOR, which is the other important thing, is the same. So for our property, they have the same consequences. So they are equivalent in this sense when S is the class of nymposition. But these two are not equivalent with respect to all games. You can find, as a challenge, you can try to find a game G, which you can give as a graph. I think there is a game, you can find a game that is not too large. Maybe the graph has like 5 nodes, I don't know. There are games not too large, so that G plus this and G plus this have different results when you do when you use the Miser rule. So that means that these two are not equivalent with respect to any possible game. And this should give you an intuition of why you shouldn't fall for just trusting the normal case for the Miser case, right? And I think that you have to know the Miser nym because it is a common special case that might appear. But yeah, handling other Miser games is super hard. Basically, that's the result of all of this. I hope you enjoy today's contest and good luck.